Yep. Okay, cool. So good afternoon, everyone. My name's McGilchrist. I work at Tarides. It's our logo up there. So this afternoon, I want to go through some of the work that we've been doing to build a homogeneous build system and infrastructure for OCaml. And it's collective work with myself and a bunch of other people that work at Tarides. And there's a long list of contributors to this work. So let's get started. So what we're trying to do is we're trying to provide a lightweight sandboxed solution that we're calling OBuilder to be able to support builds across a number of different platforms. So we want to support Linux, macOS, Windows, and the BSDs. And when we're providing that functionality, we want to avoid expensive virtualization. So we want to try and be efficient with our use of our resource. And this solution is in production, providing infrastructure for a bunch of build systems that have been mentioned already during the conference. So the checks.ocaml.io, opam-repo-ci, when you submit a pull request to OPAM, that'll run on this infrastructure, OCaml-CI, and a bunch of other systems. Okay, so let's look at our sort of stepping back a little bit and look at our requirements. So what we need to do, we're solving a simpler problem than a generalized sort of solution. So we really just need to run OCaml on many operating systems and architectures and various integrations with different continuous integration systems and build systems. I think we've got maybe about 8 different clients that are submitting builds against this. And one of the really important things that we wanted was a common build specification that we're calling OBuilder spec, for want of a better name. So as I said, we want to support Linux, macOS, and Windows and BSDs. There's an asterisk on the BSDs. We're working on that. It's not quite ready yet. And we also want to do multi-architecture. So we want to support x86, ARM64, my favorite PowerPC, S390s, and we have some RISC-V hardware in the cluster as well. That's somewhat unreliable at the moment, but that's not our fault. That's a hardware issue. Okay. So let's look at the build specification. So what OBuilder is designed to do is to take a build script and perform the steps in it inside a sandboxed environment and provide some memoization caching at each build step. So this is like a lovely S expression version of the build specification, but you can also use a Docker file. And if we look at this and ignore the parens and stuff, so it's pulling in an OCaml Linux distribution, so Alpine 315 with OCaml 414. It's doing some work. It's creating a small hello world program, compiling that program, and then in the second stage, it's also getting Alpine, and then it's copying the binary in and then running hello. So if you look at this, what OBuilder will do is each line, it'll take a snapshot before the line, execute the line. If it's successful, it'll go and save that snapshot off somewhere. And so this is sort of the core specification, and this is what the clients of OBuilder will submit to us. So stepping out a little bit, what does the O cluster architecture look like? So I thought this was important to set some context for what it sort of looks like. So we've got various clients who want to provide builds. So here I've got OCaml-CI and opam-repo-ci. And so what they do is submit these specs to the cluster. And the cluster has a number of different components. So this is kind of a simplified version of what it looks like. So as in the middle there, you've got a scheduler component. So that takes the build specs and works out how to send those to the different pools. And then you've got these various pools. So pools you can kind of think of as groups of workers with similar capabilities. And in this example, we've got an x86 Linux worker, and we've also got an x86 macOS worker. But the pools are kind of, they're an organizational thing you put on top of that. So you could organize them in a different way if you had pools that were had GPUs or some other way of organizing them, but we sort of follow operating system and architecture because that's kind of the thing that's useful to us. And then within each of those worker boxes is where we execute the build spec. And yeah, one or more workers per pool. And then the workers are responsible for executing that build spec on the platform that they're built for. So they need to be architecture, like platform specific, which makes sense if you think about it, because clearly you can't execute Linux systems calls on a Mac system. Okay. So hopefully that makes sense. So if we sort of focus in on the store piece of the worker piece of that earlier diagram. So here we've got two boxes. So this is supposed to encapsulate the entire O-cluster worker that we were talking about. So the top box sort of represents the generic scheduler, captain proto control logic sort of box. So that is common across the workers. And then in the larger box down the bottom, we've got 3 or 4 smaller boxes. So we've got a bunch of build logic in sort of a generic box, and that's functorized over the different implementations of the other boxes. And then we've got 3 other boxes there. So we've got a fetcher. So the fetcher is responsible for pulling down those Docker images. So that will go out to Docker Hub or somewhere else and pull down that Alpine 315 OCaml 414 image, which will already have OCaml installed and it'll have opam installed. And then we get to the sort of interesting bit. So the 2 boxes, the sandbox and the store, are the really platform-specific bits. And as we go through the rest of this presentation, that will be the bit that gets swapped out depending on the platform. But the interesting thing here to note is that OBuilder is a library. So if you had some reason to do something else with it and include it in a different sort of thing that wasn't an O-cluster worker, you could also do that. Okay. So let's look at the implementation on Linux. So in my notes, I've got that Linux is the obvious implementation because we've got all the things that we need here already in Linux. So for Sebastian, this is another big box, and there's 4 boxes within that. So on the top left part, we've got all that common control logic. So I've grouped the scheduler, control logic, and build logic all together. That doesn't change in between worker implementations. And then the fetcher box stays the same as well, although that could be swapped out for something else. But for our implementations, it's the same. So that leaves us the 2 interesting boxes, which is the sandbox and the store. So the sandbox is using the native runc and native containerization on Linux. So that's kind of the obvious thing because it's already there and it's already good, and it's what's used underneath for things like Docker or Podman or some other containerization solution. And that's based on Linux's native namespaces and C groups functionality. So namespaces are about isolating processes within a Linux sort of system so that they can't see each other and they're isolated. And then the C groups functionality is about applying resource controls to those groups. I think that's, yeah. And then the store is, so the store is responsible, as I said before, about taking snapshots of the state of the build. So on Linux, we have 2 different store implementations. So one is Btrfs, which uses the Btrfs subvolumes to create snapshots and store those away somewhere and to restore them back when we need them. Or we can use ZFS, which has native snapshotting support and is great. The current implementation, we're using Btrfs and the runc, but we have used ZFS, so that's quite solid as well. Okay, so that's the obvious implementation. Now let's look at the non-obvious implementations. So the Mac implementation was particularly interesting because the Mac isn't a server operating system. It's like a very consumer operating system. So it doesn't have a way of slicing up its namespaces like you do with Linux. So you don't have the C groups, you don't have run C, you don't have all that operating system support for those kinds of things. So we needed to think outside the box. So again, we've got the sandbox and store sort of boxes here. So for the sandbox, we turned to sort of the classic Unix isolation sort of policy of having user accounts. So when we perform a build, we have the build execute inside a user account on macOS, which is fine and it works, and you can add some resource controls to that and that sort of thing. So the complication for this comes when, remember, we're trying to build OCaml code. So the complication is that we need to use opam and we need to use homebrew. So luckily, opam supports multiple opam roots on a system. So we can essentially sort of switch user account and execute and tell it where to find the opam root. That's good. That's quite easy. And there's an example in the longer form of the paper that I've created. So that's fine. That works quite reliably. The second sort of less fine thing was homebrew. So homebrew wants to be installed in, I think it's user local for x86, and it's a different location for the Apple Silicon. So the documentation says that you can install it somewhere else, but we make no guarantees that it'll ever work. So, we kind of listened to them and we said, okay, fine. So what we're doing there is we're using Fuse, which is a user space file system. And what we do is we trick Homebrew into thinking that it's installed into the global space. So we wrote a little shim for Fuse that detects the user that is making the call and redirects to a particular location based on that user. So we can, Homebrew is happy because it thinks it's working in the right place, and we're happy because we can trick it into doing what we want. So that's sort of the basis of the sandboxing that we have for OBuilder. And then the store. So second point, I'll go to the second point. Initially, we were trying to use ZFS with Fuse as well. Poor Patrick, who was working on this at the time, ran into many issues with stability about ZFS, where things, either Fuse or ZFS or a combination of the two, meant that things just didn't work, or the system just hung, and or files that were supposed to be there weren't there, and a whole bunch of pain. So poor Patrick sort of had to deal with that. But sort of eventually we were like, after running this a little bit in production, we had to pull it out because it wasn't stable enough. So we sort of went back again and thought, what are we really doing with the store? Like we're copying files from some place to some other place and then wanting to restore them back. So we already have a tool for that. We've got rsync. So basically we went in there and just did the sort of naive, or slightly less, not naive, but slightly better than naive maybe, version, which is rsyncing the files between sort of the user's view of the world and a cache that sits off to the side. So that works quite well. It's not as fast as a native file system, but with rsync and being able to only copy what it needs to copy and doing some intelligent diffing, it's fast enough. So that's running for your opam-repo-ci builds. I think that's everything I had for the Mac. Yeah. So Windows implementation. So we also want to support Windows because that's quite important, and everyone uses Windows. So so we could have done a similar thing for Windows. We could have used user isolation as well, but we kind of thought it's not the most efficient sort of solution, and there's some native Windows containerization APIs and that sort of thing. So there's some facility to do that natively within Windows. We didn't use that mainly because it would take us a long time to write the bindings to be able to talk to the native Windows versions of Run C. And also because they're not stable or documented. So instead, we use someone else's work, and so we're using Docker on Windows to run the Windows builds. But we're not using Docker build, because that has a limitation where you can specify the number of CPUs you can use, but it just goes and throws it on the floor. So I think it's 2 CPUs. It might be 4, but it's a small number. So what we're doing instead is that we pull down a Windows Docker, like a Windows image that we've already built, and we start that up, and then we execute the build inside that running container. Excuse me. Yeah, and the build spec runs inside the container. So that's quite reasonable. There's a couple of different execution models for Docker on Windows. You can use Hyper-V, which is a virtualization version, or you can use a process isolation, which is more like a run C type style of thing. So that works reasonably well. It's a little bit slow to boot up because you're starting up a container. The Windows containers are, like the Windows images are really quite large. But once it's sort of warmed up, there's only a certain number that we need, and that's sort of fine. And then for the store, we use Docker technology as well. So we tag the running container, and then we store the resulting image off inside Docker under a computed key that's for that build step, and then we can restore that back later. So, I need to pause here, and I need to say that even though this looks trivial, this is written, we used LWT on top of this. In the process of writing this, Antonin found a number of bugs in LWT where things weren't implemented, or they were implemented wrong, or what was it? Inheriting file descriptors was just completely broken. We found a couple of bugs in the standard library, and we also found a bug in GNU tar, which was quite cool. So maybe it seems trivial, but we got some good results out of it. And so we're looking at, this is servicing some builds at the moment, but we want to roll it out to more. Okay, so cool. So I'll talk about some future work, because this is sort of at the top of my mind at the moment, because this is the things that we're looking at doing. So the macOS support is running in opam-repo-ci. We want to roll it out to OCaml-CI and get people being able to build things with that. And then once we've got that working and we've got a decent load on it, we'll start looking at the scaling problems and the stability problems for ZFS. So the scaling, I said that we're using multiple user accounts. At the moment, we're only using one user account, but we think we can extend that to multiple user accounts. Initially, we weren't sure what sort of resource usage we get on what is essentially Mac Minis running in the cloud somewhere. And then the ZFS stability should get us a lot of performance improvements for snapshotting. So that's the Mac. For Windows, we're doing some builds on it to produce Docker images, but we want to roll this out probably first to opam-repo-ci and then OCaml-CI. And we probably have to wait for opam-2.2 to do some of those things, but that's coming soon, I'm told. And then once we've kind of got that running and we're sort of exercising that infrastructure, we'll go back and look at the native Windows solutions. And then I promised BSDs at the beginning. So last year we started looking at a interesting project called RunJ on FreeBSD, which uses the FreeBSD's jails to provide isolation. And if we combine that with ZFS, then we can get a solution for FreeBSD as well, which will probably, we've already got ZFS, but the RunJ stuff will look very similar to the RunC stuff that we've already got. So, yeah, and there's lots of other exciting things that we can do, but that's kind of what we're looking at the moment. So I've got a LaTeX sort of version that's a longer version on that Git repo. And the two projects I was talking about, OBuilder and OCluster, are there under the current organization. So thank you.